Morning, everybody. All right, let's go ahead and get started. So today we're going to start in on Chapter 5, and we're going to start talking about stereochemistry, stereoisomers. This is a very important chapter. It's one of my favorite chapters. It has a lot of consequences in terms of things that you'll notice in terms of chemical properties of a variety of molecules, etc. So today our goals are to determine what a stereoisomer is. How does it differ from a constitutional isomer? So at the end of the day, you should be able to identify those two things pretty straightforward. We're going to talk a bit about two things that you know very well, starch and cellulose, bread and cotton kind of differences, okay? And then we'll talk about handedness or chirality. Okay? Molecules can have a handedness, just like our right hand is not the same as our left hand, even though they look very similar in a lot of respects, right? Molecules can also have this so-called handedness. And then we'll talk a little bit about what's called a stereogenic center, or a chiral center, as a lot of people call it. Okay? So first thing that we need to do is we need to build a model. So get out a single sp3 hybridized carbon atom out of your kits, and get one each of the colored spheres. So you should have a white sphere, a red sphere, a blue sphere, and a green sphere. Okay? Once you have these spheres, randomly put them on your carbon atom. Just at random. Don't even think about it. Just grab one. Don't look at anybody else. Just randomly put them on the carbon atom. So what you should have is a single carbon atom at this point with 4 different colors on it. Did we all make the same thing? Looks like we did, doesn't it? We all have a single carbon atom with a white, red, blue, and green sphere on it. But I'm going to go around and we're going to see if we made the same thing, everybody's atoms should all line up when we superimpose them, right? So if I take your model and my model, and I try to superimpose them, I see that he and I made exactly the same thing. Did we make the same thing? We did not. So one at random turned out to be identical to mine, one did not. We made the same thing. Whoop. We made the same thing. We did not make the same thing. Right? So at random, it's looking like about 50-50, right? 50-50 odds of you either having the same thing I have or something different. Right? How are they different? When we looked at the ones that were different, so let me take a look at yours again, because I know yours was different. How are they different? Huh? They're in different places. It's the three-dimensional arrangement around that tetrahedral center that's different. It's not the connectivity, right? What's the definition of a constitutional isomer? Those are molecules that have different connectivity of the same types of atoms. We have the same connectivity. All 4 spheres are still connected to one carbon atom. But how I connected them three-dimensionally was different than yours. We could only get 3 atoms to line up. I believe it was the green, the carbon, and the blue. The other 2 we couldn't get to line up, right? I have one hand of the molecule. He's made another hand of the molecule, okay? They look in terms of connectivity, identical, but they have very different three-dimensional shapes. So keep your model for now. Don't take it apart. We'll need it again later. So having things in different three-dimensional arrangements is very important, right? And so that's what we're talking about when we talk about stereochemistry. And if we look at a simple example like cellulose and starch, we know intuitively from our everyday experiences that these are very different molecules. Cellulose and starch are nothing more than sugar linkages. Okay? They're polymers of glucose, both of them. However, if you look at cellulose, what you notice is that this oxygen linkage, or an ether linkage, if you will, that's connecting these two sugar molecules together, it's an equatorial bond. Remember last time when we were talking about six-membered rings, we had equatorial and we had axial, right? So this is an equatorial linkage, whereas in starch we have an axial equatorial linkage. The connectivity's the exact same, but how it's oriented in three dimensions in space is very different. And so this gives rise to different physical properties. What are some of the different physical properties between cellulose and starch that you know of? Okay, cellulose is more fibrous, starch is not. Okay, good. What else? What else do you know about? We do eat cellulose, actually. We don't digest it, that is true, right? But we can digest starch. We can get energy from starch. We eat bread, we get energy. We eat a salad, not so much, at least from the lettuce, right, because it's mostly cellulose. Cellulose is one of the most abundant materials on the planet, right? It's made up of sugar. We should not have a food shortage on the planet because of that, but the problem is we can't digest it, right? But we can digest starch. All because we go from having an equatorial bond. We don't have an enzyme in our gut that can process this polymer. We do have an enzyme, however, that can process this one. That's why we can digest it, right? And so they have very different chemistries. If you look at a three-dimensional structure of both of these molecules or both of these materials, you'll notice that cellulose has kind of a sheet structure with extensive hydrogen bonding networks that hold it all together. Okay? Your paper that you're writing on right now is made of cellulose or starch? It is made of cellulose. Go to the water fountain, take a cup of water, pour in it. It will wet, but will it dissolve? No. Take a little bit of starch, put it into a glass of water and stir it up. Will it dissolve? Yes. You'll have to stir it a little bit, but it will dissolve. Very different chemical properties, okay? So, neat little tidbit. Everybody know about the spy planes that back in the 60s and 70s when they had to fly over Russia and all this stuff and take reconnaissance aircraft? The maps were actually published on starch-based paper. Can anybody tell me why?
Because if they got caught, they could just throw water on it and dissolve it.
They could eat it. Or if they crashed into a lake or a river or a stream or the ocean, the maps would dissolve. That's exactly right. So it was a great way of getting rid of your evidence using the chemical properties, right? And so if we look at amylose, which is just one form of starch, which has this axial equatorial bonds, this is the type of stuff that you'll find from wheat. You'll find it in bread. You'll find it in these specialized maps that were made for spy planes, right? All that kind of stuff. Very different physical properties. However, if I take this molecule and I hydrolyze it, that is, I put it in water and I heat it up with a little bit of acid, I can break it down, and I will break it down into glucose. If I take cotton, if I take cellulose, and I do the same thing, I place it in water with a little bit of acid to catalyze it, and I heat it up for a long time, it will partially degrade into glucose. The same molecule. I have the same molecule, but when they connect, they're connected differently. Well, they have the same connectivity, but it's the three-dimensional arrangement, right? So here we have equatorial type bonds. You would have no problem wearing a cotton shirt. Wearing it one day, it gets dirty, you take it home, you put it in the washer, put it in the dryer, you have a clean shirt to wear the next day, right? If it was a starch-based shirt, you couldn't do that. You would wear it, and you would throw it away. or you would wear it and it would dissolve throughout the day as you sweated, okay? Not a particularly great way to make an item of clothing, okay? So, three-dimensional arrangement of atoms matters. That's the point. Structure matters. That first lecture that I gave you at the beginning of the semester, I told you everything is about structure, right? Structure matters here. And so there are going to be two classes of isomers that we need to focus on today. One is constitutional isomer, and the other is stereoisomer. Some things that you need to know about constitutional isomers: they have a different constitution. They have the same number and types of atoms, but they're connected differently. And as a result, right, they will have different IUPAC names, okay? They may have different functional groups. They will certainly have different physical properties, and they will have different chemical properties, okay? Constitutional isomers have a lot of things that are not the same. Stereoisomers, however, differ only in the way the atoms are oriented in space. They will have identical IUPAC names with the exception of prefixes like cis or trans or RNS, which you all probably learned about in lab the other day, right? And we'll learn more about it in class on Monday, okay? They always have the same functional group. If you see two molecules that have different functional groups, they cannot be stereoisomers by definition. Okay, it's an easy way to determine. Do they have the same functional group? Yes. Maybe they're constitutional isomers, maybe they're not. But if they have different functional groups, they are definitely constitutional isomers of one another, okay? When we have a particular three-dimensional arrangement, we call that a configuration. When we were talking about Newman projections, was that configuration or conformation? That was conformation. And conformation and configuration sound a little bit alike, but they are different. Conformation is how things are oriented in space by result of rotation around a sigma bond. Conformation is about a sigma bond. Configuration is about how things are permanently located in three-dimensional space, not about rotation around a sigma bond, okay? So let's do a quick little concepts test. We got a green pair, a blue pair, and a yellow pair there. Tell me whether or not each of those pairs are constitutional isomers with respect to one another or stereoisomers with respect to one another. The green pair, they are constitutional. I noticed that there are the same number of carbons, the same number of hydrogens, but they are connected differently. If I was to name the one on the left, how would I name it? What's the parent? It's a pentane, right? And so what would it be? 2,3-dimethylpentane. 1, 2, 3, 4, 5. 2,3-dimethylpentane. What about this one? That is 2,4-dimethylpentane. Different names, different connectivity. Both hydrocarbons, both isomers of one another, but those are constitutional isomers. Is the functional group different between those two? No. So they have the same functional group in terms of being alkanes, but they have different connectivities. How about the blue pair? Those also are constitutional isomers. That one's pretty obvious when you just look at it, right? What's the thing that stands out that's different about them? The functional groups. The one on the left is a ether. Yep. And the one on the right is an alcohol. We have an ether and an alcohol. Very different functional groups. Not identical at all. They must be constitutional isomers of one another. Okay? How about the yellow pair? They are stereoisomers. The connectivity is exactly the same. Let's not worry about the prefix cis or trans yet. If you were to name the one on the left, how would you name it? Not cubane. Cubane is a three-dimensional structure. Cyclobutane, right. So this is 1,2-dimethyl cyclobutane. How would we name the one on the right? Same, 1,2-dimethyl cyclobutane. But how would we distinguish the one on the left from the one on the right? We have to use an additional prefix. These two methyl groups, this solid wedge means what? It's coming out of the plane of the board towards you. And what about the dashed wedge? It's going behind the plane of the board away from you. So these are trans to one another. So we would say these are trans, or this one is trans 1,2-dimethyl cyclobutane. What about this one? That is cis 1,2-dimethyl cyclobutane. Will they have the same physical properties? They'll have similar physical properties because they have the same functional group, but not necessarily identical. They will have different boiling points. It's slight in this case, but they can have different physical properties, okay? Just like starch and cellulose have different physical properties. One is soluble in water, the other is not, right? So we can have different physical properties from the stereoisomers. Okay? So let's look at a couple more examples. Here we have 2-methylpentane and 3-methylpentane, right? Those are constitutional isomers of one another. We've just moved the methyl group from position 2 to position 3, right? They have the same molecular formula that you can see up there, C6H14. They do have different boiling points. They have different melting points. They have slightly different IR spectra if you look down in the fingerprint region, okay? But they are constitutional isomers of one another. The molecules on the right, we have this situation where we have cyclopentane as the parent in both cases. The methyl groups are attached at carbons 1 and 2 in both cases, but one has those methyl groups in a cis relationship, and one of those has those methyl groups in a trans relationship, okay? So they have the same molecular formula, the same IUPAC name, except for the prefix that comes out in the beginning, and so they are stereoisomers with respect to one another, okay? Now, molecules can have what we called handedness, and that's what we looked at here when we built our model. You and I had the same handedness. You and I had opposite handedness. So we don't know how to name them yet, although you did cover it a little bit in lab the other day. But you and I will just call it the right hand, and I had the right hand and you had the left hand. Okay? The connectivity was the same. The functional groups were the same. The functional groups are just a red sphere, a white sphere, a blue sphere, and a green sphere. Whatever they mean, right? Connectivity was exactly the same. So some molecules are like hands. Our left and our right hands are mirror images of one another. If I hold up my right hand to a mirror in the morning, what's reflected back at me? My left hand. If I hold up my left hand to the mirror, what's reflected back? My right hand, right? My left and my right hands are mirror images of one another. But I cannot superimpose one on top of the other. Right? And we know that our right and left hands are very different. Even though I've got 5 fingers attached to this palm in both cases. Many of us are right-handed. Some of us are left-handed. What does that mean? What does that mean? Why can't I just use my right hand for everything or my left hand for everything? Why? Okay, that's true. If you go and pick up a hammer, does it feel the same if you pick it up in your left hand or your right hand? It doesn't really feel different. But what about if you grab a pair of scissors? That feels different, doesn't it? Actually, you have right-handed and left-handed scissors. It matters. If I give you a baseball glove and I tell you to put it on, and I say, just put it on any hand, does it fit either hand? No. My baseball glove fit my left hand, right? For some of you, you needed a right-handed baseball glove or softball glove, whatever the case may be, right? It won't fit the same. Okay? So molecules can have this same type of relationship, okay? This idea of being chiral, okay? Chiral, handedness. What does achiral mean? It's the absence of handedness. Not all molecules have handedness. The molecule that we just built with the 4 different colored spheres on a carbon atom has handedness, okay? But not all things have handedness. For example, socks, unless you're talking about the socks that some of you wear that have the places for your toes, but just regular old tube socks. Does it matter if you put it on your left foot or your right foot? Not at all. It's because they are achiral. Socks are not chiral, okay? And so it doesn't matter. The assembly line for making tube socks does not have a left-footed line and a right-footed line. They just make tube socks, and at the end they have a machine or somebody that just takes 2 of them and folds them together and calls it a pair. Okay? That is not true for baseball gloves. You have 2 separate lines in an assembly line that make a left-handed, and then you have a line that makes a right-handed because they are different. Okay? So if I take a left sock and a right sock, you'll see they are mirror images of one another. But I can take the left sock and I can overlay the right sock right on top of it. It's perfectly superimposable. So if a molecule and its mirror image are superimposable on one another, it is achiral. If a molecule and its mirror image are non-superimposable, they are chiral. So our hands are chiral. Our feet are chiral. Okay? Let's look at some other normal objects that you might be familiar with. A glass like a Brandy Snifter. Is it chiral or achiral? It is achiral. And why do you say it's achiral? It does have symmetry. That's a good observation, right? In fact, it has a mirror plane of symmetry that runs right through the middle of it. Mirror planes of symmetry must be absent in molecules or objects for them to be chiral. Okay? A Brandy Snifter is an achiral object. You can take one Brandy Snifter, another Brandy Snifter, and you could, in theory, overlay them. Physically you can't, but if you imagine doing it virtually, you could overlay one on the other and they would become an identical object. Okay? How about a boat propeller? Is that a chiral object or an achiral object? It is chiral. It is very much so chiral, and it's because the boat propeller, the blades come out and twist in one direction. Okay? Does it matter for your boat that it's chiral? You bet. You buy the wrong chirality of boat propeller, you put it in forward and you'll go in reverse. Kind of mess you up, won't it? The boat propeller and the way that the blades come out matters. Okay? So chirality is important for things other than just organic chemistry. Right? You buy the wrong chirality of the boat propeller, your transmission's not going to know. It's not going to give you the right direction anymore. How about a pair of shears? Chiral or achiral? They are chiral. And when you go and buy a nice pair of shears, not the cheap little scissors that they give kindergartners, okay, but a really nice pair of scissors, they have left-handed scissors and they have right-handed scissors. Right? And if you've ever seen a lefty person trying to use a pair of right-handed scissors or vice versa, it's painful to watch. It doesn't work. Right? It doesn't really work very well. Okay? Shears are chiral. How about a hammer? How many of you have ever gone to Lowe's or Home Depot and said, "Where's the left-handed hammers?" The guy's going to look at you like you're crazy. There are no left-handed hammers. Could I make a left-handed hammer? I could probably make one, but it's not common, right? You go and you get the hammer, whether you're a right-handed person or a left-handed person, you buy a hammer. When you go to the place that sells scissors, you can ask them for right-handed or left-handed scissors. It matters. Why is a hammer not chiral? Why is it achiral? That's right. So the claw, right? So if I turn it this way and I look down the claw, there's a mirror plane of symmetry that between the left-handed side and the right-handed side. And so that plane of symmetry that we have means that we can't have a chiral object. How about a baseball glove? We've talked about that one already. It's chiral. Take a right-handed baseball glove and hold it up to a left-handed baseball glove. You'll see that they are mirror images, but they are not superimposable, just like our hands. Okay? So now let's take our model again, and this time leave the white and the red exactly where they are, okay, and remove the green and replace it with a blue. Yep. Now, did we all make the same thing? Let's do the experiment. We did? But we did before. Now, we made the opposite before, right? Now we have the same. We have the same. We have the same. I think we've done enough experiments here to determine that, in fact, we've all made the same molecule. So what can you derive from that little experiment? For something to be chiral, for a carbon atom to be chiral, how many things must it have around it that are different? 4. If a carbon atom has 2 identical things, can it be chiral? No. So if a carbon atom has 2 or more of identical things attached to it, an sp3 hybridized carbon atom, by the way, we'll see examples that are a little different later, but for an sp3 hybridized carbon atom, if we have 2 identical atoms attached to it, it can't be chiral. Okay? Why can't it be chiral? What's here that keeps it from being chiral? The symmetry. That's exactly right. There's a plane of symmetry that runs right through this molecule. And a chiral molecule cannot have a plane of symmetry. There are 2 things that a chiral molecule cannot have, okay, at the basic level. They cannot have a mirror plane of symmetry in them, nor can they have an inversion center. We'll talk about what that is in a minute, okay? In reality, they can't have an improper rotation axis, but I don't want to get into that. As a result of that, that means they cannot have a mirror plane of symmetry, and they cannot have an inversion center, excuse me. Okay? So, here we've got water. Water is achiral. The oxygen atom has 4 things around it. 2 of those are hydrogen, 2 of them are electron pairs. It does not have 4 things around that central atom. It is achiral. You take one water molecule, you take another water molecule. They are mirror images of one another, but they are perfectly superimposable. I can superimpose one water molecule onto another. If I look at bromochloromethane, it has a mirror image, but again, I can overlay everything perfectly. It is not a chiral molecule. Okay? So let's think of some things that we need to commit to memory. In general, a molecule with no stereogenic center will not be chiral. A stereogenic center is a carbon atom, or an atom, in this case we're talking about carbon atoms, that has 4 different things attached to it. You will quite frequently hear me call those chiral centers. Chiral center and stereogenic center for all practical purposes are nearly identical. Okay? If a molecule has 1 and only 1 stereogenic center, the molecule will always be chiral. Repeat that for me. That's right. So if I look at a molecule, no matter how big it is, and it has 1 stereogenic center, I know it's going to be a chiral molecule. If a molecule has 2 or more stereogenic centers, the molecule may or may not be chiral. Okay, so if I see a molecule that has multiple stereogenic centers, it may well be a chiral molecule, but it's not necessary that it be chiral. One chiral center, real easy. Two or more, you got to do a little thinking. If a molecule contains a plane of symmetry, it will be achiral. Chiral molecules cannot have a plane of symmetry. They cannot have a mirror plane, and they cannot have an inversion center. They can have rotation axes, but they cannot have mirror planes. Okay? And a plane of symmetry is a mirror plane that cuts the molecule somewhere in half. Okay? So that one half of the molecule is a reflection of the other half. The mirror plane does not have to go through an atom. The examples that we have right now that we've shown, the mirror plane goes through atoms. But it is not necessary. It can go through bonds. Okay? It just has to be a mirror plane. Okay? So to be chiral, if you know that a molecule is going to be chiral, what does it have to have? A single stereogenic center, a single chiral center. If it has more than one stereocenter, maybe, maybe not. Right? Can't contain mirror planes. Right? And if a molecule contains no stereogenic centers, generally it's not going to be chiral. But we'll see some exceptions as we move forward in the chapter. Okay? So, for example, if we look at bromochloromethane, right, that's exactly what we just built here. We can clearly see, let's see, they did it this way. Okay. We can clearly see the mirror plane, just like they have there. Contains a mirror plane, cannot be chiral. Because it contains a mirror plane, no matter how you put those atoms together, each and every one of us, if we took our model and went around, they would all be identical. Every one of them. Okay? However, if we take one of the hydrogens off of bromochloromethane and replace it with a fluorine, so that we have bromochlorofluoromethane, that's starting to become a mouthful, right? It would no longer contain a plane of symmetry, and it would be chiral. Okay? That would be the example that we started out with, where we had the 4 different colored spheres around our carbon atom. Okay? And so you can see the plane of symmetry. How many of you, when you took general chemistry, were comfortable with symmetry? Mm-hmm. Did you all talk about symmetry when you started talking about Lewis structures and you built models and you looked at different things? You saw that things had symmetry elements, right? Things like inversion centers and mirror planes. You saw the symmetry in those molecules, okay? You're going to need to be able to look at things in 3 dimensions, okay? We represent these molecules on 2-dimensional surfaces, but they are actually 3-dimensional objects. Your model kit is there to help you with that. You all will try to do this in your head. Do not do that. Okay? With a simple little 1 carbon atom that we're dealing with today, you can do that in your head after about 2 or 3 weeks without messing it up. Now add 10 carbons. Maybe 20 carbons. It gets more and more and progressively complex to keep track of that in your head. Your model kit is there to help you. Okay? So, we know that a stereogenic center is going to be a molecule that has a carbon atom with 4 different things attached to it. Here's a couple of examples that are kind of common. This is Darvon. It's an analgesic. What's an analgesic? Pain. Yeah, it relieves pain. It's a pain reliever, right? It contains 2 chiral centers. These 2 carbon atoms right here are stereogenic centers. It's got a benzene ring. It's got a CH2. It's got an oxygen that's part of an ester. And it's got another carbon atom that's clearly different than this CH2. 4 different things around that carbon atom. It's a stereogenic center. And one of the things that we do when we're trying to identify stereogenic centers is we will put an asterisk or star them. We say we star the stereogenic centers. Okay? This carbon atom adjacent to it is also a stereogenic center. It has a methyl group. It has this carbon atom, which is clearly different than this carbon atom, and it has a hydrogen. 4 different things around that carbon atom, 2 stereogenic centers. So is this molecule chiral or achiral? Or can we determine? It may be chiral. It turns out it is. But to do it, you would have to build the model. You would have to ask yourself, once you built the model, does it have a mirror plane of symmetry? In this case, it does not. So it is a chiral molecule. But according to our rules, if something has 2 or more stereogenic centers, it may or may not be chiral, right? Ephedrine. What do you all know about ephedrine? Take it when you get a cold. You all probably know about pseudoephedrine. What do you know about pseudoephedrine? Can you just go and buy it anymore? You do make meth with it. I hope you don't make meth with it, but you can make meth with it. Right? Ephedrine and pseudoephedrine can both be used to make methamphetamine. You just have to remove the OH. Notice it has 2 chiral centers. This carbon has a hydrogen, an alcohol, an aromatic ring, and a carbon. 4 different things. This carbon atom has a hydrogen, a nitrogen, a carbon, and another carbon, a different carbon that's clearly different. 4 different things. Is ephedrine chiral, achiral, or maybe? It's a maybe, according to our rules, and it turns out it is chiral. Okay? And fructose, a real simple sugar that a lot of us like. Notice it has 3 chiral centers. Mother Nature's really good at making chiral centers and putting atoms exactly where they need to be in nature. Okay? We're still struggling with it in the lab, but we can do it. 3 continuous chiral centers in fructose. Carbon with an OH, a hydrogen, a carbonyl, and another carbon. 3 of them. It's got 3 chiral centers. We would mark those with a star. So, chiral, achiral, or maybe? Maybe, but I know it's chiral. It exists in nature as a single hand. Mother Nature makes it as 1 hand and 1 hand only. Well, for the most part. 1 hand only. Okay? It's a sugar. It's a very simple sugar. Okay? Your model kit building skills are going to come in very much so handy when you are doing problems. When I'm asking you to draw both enantiomers of a molecule. Don't worry about the word enantiomer. You should have been exposed to that in lab. We'll talk more about that on Monday, right? But for right now, we've got structure A and structure B. Are they identical or different? Are they stereoisomers or constitutional isomers? They're stereoisomers, right? And so if we needed to draw the molecule, right, on the left and on the right, we might struggle with that, but building our model will help us. How would you start to build that model on the left, model A? Describe for me in words how you would do that. What would you do? You would start with the center? Okay. That's nothing wrong with that. And what would you do? Okay. If I was taking a test, what I would immediately recognize is that that's going to be a chiral center. And do I have enough time to put all the carbons together? Here, probably I do. But if it was a little bit bigger, I might not. So what I would do is I'd actually take 4 colored spheres, and I would give them a name. So I'm going to call hydrogen is almost always white. Oxygen is almost always red. And then pick the other 2 colors for what you want to be the methyl group and the ethyl group. Okay? So let's say the green is the methyl group and the blue is the ethyl group. So if I have this sitting like this, right, where would I put the hydrogen if I'm holding this carbon atom? Where would I put the white one? I'd put it behind the plane, right? So there's the plane. So there's what's coming towards me. There's what's going back. The hydrogen is going away from me. I would put the white on. Where am I going to put the red one? I'm going to put that towards me, right? That's coming towards me. And then what did we agree to? We agreed green was the methyl group, right? So how would I draw that? I would put the green one on top, and I would put the blue one over there on the right. And I would have my molecule, right? I would have this enantiomer. How would I then draw this one? Do exactly the same thing, but really what I can do, right, is I can just swap two groups. And when I swap two groups with a molecule that has only one chiral center, I get the other stereoisomer. Any two groups, if you swap them. So once you draw one, swap two, and you get the other stereoisomer. Always, every time. Okay? If we look at this molecule, what we recognize is that each carbon atom has four different things attached to it. This carbon atom has a white sphere, a green sphere, a carbon that has a white and a red that are oriented differently than this carbon atom. This carbon atom, the red is up and the white is back, although it's hard to see, right? So you might think that that's a chiral center, but it's not. Okay? It turns out that this molecule can't be chiral because it has an inversion center, or center of symmetry. Okay? So notice if I start at one of these white spheres, and I go through the center of the molecule in this case, and go out an equal distance from the center, I end up at an identical element. So if white means hydrogen, I'm going from hydrogen through the center, an equal distance to another hydrogen. If green means fluorine here, notice that I would go from a fluorine through the same center, equal distance out, and I would end up at a fluorine. It has a center of symmetry. It cannot be chiral. Okay? So if we have molecules with centers of symmetry or with planes of symmetry, mirror planes, we can't be chiral, right? So let's look at an example. If we look at methyl cyclopentane, carbon number 1, is that a stereogenic center? It's obviously not because it says so, right? But why isn't it? Because we have two identical groups, right? But more importantly, if you built the model, you would also see that there's a mirror plane of symmetry that goes right through these three atoms through the center of the molecule. Okay? However, if we change one of the groups, so in this case, put an alkene over here, now we do have a chiral center, right? Because this carbon's attached to a methyl group, it's attached to a methylene, which is a CH2, it's attached to a hydrogen, and then it's attached to an alkene carbon. Those are four different things. This carbon is a stereogenic center, okay? Chiral centers can be parts of rings. Where's the chiral center on that molecule? The CH. That is the chiral center. Okay? And what we do when we look at that, we notice that it's attached to a hydrogen. It's attached to a methyl group. It's attached to an OCH2, but it's also attached to a what? A CH2O. So going this way, it's connected to something different than going that way, right? Even though it's part of a ring. It's okay to be part of a ring as long as the ring contains four different elements, so to speak, as you go around it. Okay? This has a lot of practical consequences. This is an example that's actually pretty severe. So many, many, many years ago, probably back in the 60s, I don't remember the exact date. One of the things about being pregnant is women typically have a lot of morning sickness, and it's not particularly pleasant, and they would like to have something to help treat that. And it turns out that this molecule called thalidomide was very potent at treating nausea. A pregnant woman could take thalidomide, the nausea would just kind of dissipate. They could go on about their day. Okay? The problem is that thalidomide is chiral. It's got a chiral center. Okay, one stereogenic center. It's got mirror images that are non-superimposable on one another. It turns out that this particular hand of the molecule does really great at the anti-nausea stuff. This hand of the molecule is a teratogene. Does anybody know what a teratogene is? It does. And babies were being born with little stumpy limbs and deformed faces and skulls. It was horrible. Okay? Because of how these two atoms, this nitrogen and this hydrogen, were oriented in 3 dimensions. You go from anti-nausea to birth defects. And they were making this drug in what we call a racemic form, meaning it contained equal quantities of the left hand and the right hand, because it's the easiest thing to do. It's the easiest way to make a molecule. Okay? If you look at sucrose, sucrose has a lot of chiral centers. Mother Nature makes sucrose as only one stereoisomer, even though they've got all those stereo centers. That's pretty impressive. Mother Nature is actually a pretty darn good chemist. Taxol, or paclitaxel. Anybody? It's an anti-cancer agent. This is a very potent anti-cancer agent. Back in the 90s, there was a big, big push to try to be able to synthesize this molecule to where each chiral center is exactly in the right 3 dimensions, because if it's not in the right 3-dimensional arrangement, it doesn't work. And there was a big push for chemists to be able to synthesize this molecule. Can anybody tell me why? Turns out Taxol is found in the yew tree, and the yew tree is endangered. And so to treat a handful of cancer patients, we would have had to wipe out that species of plant, literally, because it doesn't make a whole lot of it in any one tree. It's a very small quantity. So the only way that we could practically use this as a cancer treatment is to synthesize it, starting from crude oil. It's many, many steps to make it. That's why it costs an awful lot of money. So why don't we just go out and grow more yew trees? Because you can't. You can't take up the entire earth with a forest of these yew trees, right? Then you have other problems, right? So chemists spent an awful lot of time figuring out how to put this molecule together with all these stereogenic centers in exactly the right location. It wasn't an easy task. Okay? So your sapling homework is available for Chapter 5. Get started on that. Start reading ahead. We'll continue with this on Monday. Turn in your inverted lecture on your way out, and have a great weekend.